In the previous class we have seen the logical operations, which were bitwise logical operations, and we have said that their main usage is directed towards thresholding of images and manipulating of image masks. Now for this class I have chosen this image of an apple, and we are going to first convert it to grayscale image. Fix the visualization. Here it is, and we are going to perform some thresholding operations on this image. There are the main thresholding operation for images is this one. CV2.threshold, which takes a grayscale image, and always a grayscale image, so we have the image converted to grayscale M. Then it takes a threshold value, so the threshold would be some value. Let's go with the middle, 128, and it takes the max binary value of the image, 255, and then it takes the threshold type, which type of threshold we would like to use, and the threshold type can be binary threshold, I think it was CV2 binary, like this, and let's visualize the result. An error. The threshold returns two results. Here it is. So if we separate the image on 128 as a threshold and 255, we would have, using threshold binary, binary image here, which separates all of the values above 128 are considered white, and all of the values below 128 are made black. There are other types of thresholds, like binary, I think it was like this, inverted binary, which means that we have binary threshold, but all of the values, pixels below 128, are set to white, to the maximum value, and all of the pixels above are set to black. So it creates the threshold image, but immediately inverts the result. The idea here is to have some sort of segmentation of the image based on the color values. It is expected usually that the background would have different coloring than the foreground. So here the foreground is darker, the background is lighter, and performing threshold gives us foreground background segmentation in a way. But it is also used for other places where we want to separate the color. So we can reduce the value here, like 50, and we are going to get different results in the image here, and let's say 200, much different result here. Even the shadow became part of the image. There are other flags that can be considered. Threshold binary and threshold binary inverted are the most used. Then we can have threshold, I think it was like this, truncated. So it truncates the images. And to 0, it will set all of the values. I think it's let me check the flags. So it was connected. 0 is connected. So all of the values which are below the threshold are set to 0. Either is to 0 inverted. All of the values above the threshold will be set to 0, and the other pixels will keep their value. And I think we saw trunk. It truncates the values of the pixel to the value 128. Everything that is above this value is set to 255. So basically the image pixels are truncated to the pixels value of 128. And there is another threshold that can be used. It's called Otsu. It uses some sort of optimization algorithm to automatically detect the threshold in the image. I think it was some expectation maximization. I think on the theory classes you have probably covered Otsu, or you can read about it more. Its value is returned, the value of the threshold is calculated and is returned in the function threshold, and that is why the function threshold actually returns two values. So here it is. It detected that 163 is the optimal threshold value, and the Otsu threshold will make the threshold, calculate it, and then create a binary threshold. So practically what we had are, let me just have them all here in the notebook. So we had threshold binary, we had threshold binary inverted, we have truncated to 0, to 0 inverted, and we have Otsu threshold. So I'm going to have this binary inverted, not like this. Truncated to 0, 0 inverted, and we're going to have Otsu, and I'm going to show all the images. So the last value will be printed. A better approach is probably to use a for loop here, because these are actually from 0 to some value, but I'm not certain about their exact value. Maybe we can print them. To see their actual values, because they are simply some integer values that in the implementation of OpenCV would tell the function which algorithm to use. As you know, OpenCV is open source, so you can actually see the implementation of threshold. Did I set to everybody? No, to 0 inverted and Otsu. So here it is. So here are the flags 1, 0, 1, 2, 3, 4, and 8. And we have the image of apple with each of them. And the calculated value using the Otsu threshold method. So thresholding would be the most used operation in my opinion. You will always need to perform some thresholding sometimes to get the most white or the most dark region of the image. You would use this operation. As you can see, it's available in OpenCV. It will return a binary image in most cases. So mostly this one, threshold binary, will return binary image. Truncated to 0 and to 0 will return grayscale image, and also will also return a binary image. If you don't know the value that you would like to set for the threshold, then you would use probably also thresholding. And you can experiment with different values if you would like, with different images. Just before using thresholding, make sure that the image that you're using is actually previously converted to grayscale. If it's not, you're going to get an error. Okay, so we get the threshold images. Next thing we would like to do is go to another thresholding function. And this function is adaptive threshold. So this function will cover the cases where the image is not lit with the same light intensity everywhere. So we're going to test it on the apple also to see the result. I'm going to write the image adaptive threshold. It also takes the first will be argument is the image, then we have the maximum value, then we have the type of adaptive thresholds. There are two types of adaptive thresholds. One is CV2 adaptive threshold mean C, and the other one is threshold Gaussian C. So let's take the first one, adaptive C, and then the type of threshold that we want as the result. Let's go with binary threshold, and what we have next is the dimension and the difference between the pixels that we would like to have. So we have a constant that is subtracted from the mean or the weighted mean, which is calculated. So this gives the type of calculation. The mean is the mean value of the pixels in a given distance around the pixel that is being calculated. Gaussian is a weighted mean, which gives a Gaussian distribution over the center and gives more importance to the central pixels than to the pixels in the periphery, which means that it calculates some sort of a weighted mean, which gives weights to the pixels in their contribution to the mean, and C is the constant that is subtracted from this number. So what we give as argument is two numbers. The first number would be the radius, so let's go with something, and another value 10 to be the difference between the values of the pixels. We copy from above and see the result. Here is the apple. If I increase this to, let's say, 100, okay, it needs to be odd number. You can see that the thresholding takes a larger area. If I go, let's say, with 301 to take most of the image, we would get the similar result. Let's say 601 to get the full image. You get the same result as the above image, which means that when we are doing threshold in the image, it does the threshold by a fixed value to the full image, and here it does the threshold, adaptive threshold, calculated for the radius that we give around the pixel. So the smaller the radius, the smaller the area that is affected. So if we go with 11, we get 11 pixels radius, and as you can see, we do some sort of edge detection, because it will take the mean value of the images in a 11 pixels by 11 pixel area and will mark white all of the pixels that are less than 10 difference of intensity, and all of the other pixels will be marked with black. As you can see, the most pixels that are getting changes from the mean value are the pixels that have some sharp change in their value, and that's usually on the edges of the objects. This is also used for thresholding in images where the lighting is not quite even, which means that if we had a gradient in the background color of the apple here, then this adaptive threshold will be more useful. If we have a clean image like the one of the apple, then the normal threshold is fine enough. We don't need to use the adaptive threshold on the image. So these functions basically cover the thresholding. We had the Otsu threshold that makes some optimization. It is actually tries to maximize the difference between the classes and minimize the within class variance of the pixels, and that is why it works good for some images. And we had the thresholds with the fixed threshold that we set. If we set a different values for this threshold, we're going to get different images. Here the value is not important. So what we get is different images, as you can see. Otsu is the same image, but for the others, and also the maximum value, if we set it, let's say 180 or something like that, it will calculate, I think, the maximum value of the image to be on 180. It again doesn't make much change for Otsu, and adaptive thresholding will be used where we need to, where the background and the foreground are not even, but there is a gradient in the image. Let me try and find an image and copy it that can be used for gradient. So let's load this image here. And read. This will be the image. Let me show the image how it looks like. So I'm going to load it as a grayscale immediately so that I can visualize it here. M2. And what I need is to do another result. I'll do an Otsu threshold here for the image. Image we have here there is an error. For the Otsu it was threshold Otsu. Okay, and then get the result 2 and the result together. So I copied the wrong image. We do a cut paste. Okay, now this should work. I get an error. What's the error? Threshold had 2 results. I always forget about threshold having 2 results. Here it's image 2. Here it is now, maybe with a lower value it will get better results. Yes, it does get better results. So as you can see, here we can do the thresholding in an adaptive manner because the image is not lit equally everywhere, but it saves our image nicely here when we need to process now this Sudoku, because here we have an image of the Sudoku, and now this is probably for some OCR task where we need to identify which are filled, which are not, and then fill them in the image automatically. Identify which number it is, and then fill it in. What's important is that these masks that we get with the thresholding we have this image. Maybe I can get two results, like result 3 is bitwise or from result and result 2, and then show it. Here it is. You can combine these masks. So practically you can do different thresholding, like for example for the apple. Let's go with the apple and get the threshold. I'm going to use a new one. The apple was in image 1, and I'm going to do two thresholdings, binary and binary inverted. So these two will be done on the image, and I'm going to set threshold binary for, let's say, 128 and binary inverted for 77. Leave it at that, and then do result is bitwise this will give me all of the pixels. White will be above, this one will be, this will make everything below 128. So I should switch 77 and here 128 bitwise or end bin and bin inverted, and then show the result. The idea here is that I would get two thresholds and combine these images. Here it is. As you can see, it will give me white for all of the pixels that are between 77 and 128. We can also use the in-range function. I think it was like this, from in, and we needed to set low 77 128 and then show the result 2. You get the same result. So this is another thresholding function that gives us the value of the pixels which are between some low value and some high value, 77 128. Unlike the thresholds, in-range can be used with 3 color images, so I'm going to read the apple again here, but I'm going to read it with 1, and this will be in IMC, and copy this in-range function, but now instead of these values I'm going to use tuples like 77 100 150 128 150 200, and this will take me ranges for each of the color channels. I would like to see the image with color. Sizes of input arguments do not match. Aha, my mistake. I used it on a wrong image. I should have used it on IMC. And here is the in-range function, what it did. Maybe making bigger values here, here, here would give me a bigger image. Here it is. Unfortunately, I didn't change it, so IMC is RGB to BGR. We visualize IMC first. Okay, here's the apple. And when I calculate the in range, I'm visualizing result 2. And it does something strange. Let's check. It probably gives the masks and combine them for each of the channels. So it sets the images and they combine. Okay, and what else was important here? Yes, this in range and thresholding is also used nicely with the HSV channel. So let me just find an image of a head somewhere. I think I had Lena, so I'm going to load it. No, I don't. It's in a different folder. Okay, let's just go with this one. Okay, here it is. This will be the image. It's not Lena, but it's close. So let's try and convert it to HSV. Here, and then we will perform thresholds for the values within range. So we have hue, saturation, and the value. I'm going to take these two hue. No, I need some threshold for hue, but saturation and value will go from 0 to 255 because we are not interested in the saturation and the value, we are interested in the hue. And let's try, let's say 60 to 100 hue. I didn't visualize the result. Okay, it's a nice image, obviously. Let me check 120 to 160. I really don't remember the exact values for skin. 110, 100 maybe to 160. Here it is. I got the skin out. So we did the segmentation maybe a bit lower. I don't know, to get the hair out. 120, 110. Okay, never mind that, but we get the head and the skin nicely segmented. This is now for BGR image, but for HSV we can do a good segmentation of the skin. Otherwise, for RGB images it will be very difficult because you're going to need to get the range of R channel, B channel, and G channel. All of the three channels will have different ranges for the threshold. You're going to need to tune them all, and here we only tune the hue value, which is the radial value. It's like the angle of the skin. 120 is better. And the other values are not important, from 0 to 255. We are not thresholding based on them. We can actually perform a threshold of the image if we want to do a binary threshold just on the the value channel of the color space, because this is the actual grayscale representation of the image. This channel gives the light of the image, the saturation gives something different, and the hue gives the actual color. The saturation gives somehow the intensity of the color, whether it's more in the grayish area or if it's more, so to say, emphasized the color. So I think this is it for this class.